Thank you. I hope everyone has been revitalized by a little bit of coffee and are ready to start talking about Pluto again. So I'm going to be the first of these two joint talks, and while I have just my name up there on the slide, like James said, this talk is really an amalgamation of work by a lot of different people. Much of it is from a paper that I co-authored with Leslie Young, Ji Zhang, and David Nesvorny, but I'll present some work from other people as well, and so hopefully I've done my best to present it accurately. But yes, wanted to make sure I was clear that this was a group effort. So I'm going to talk about Pluto's volatile inventory, and specifically the volatile loss processes that have been active on Pluto from its formation all the way up to the present day. So I have this little graphic just to kind of organize what we'll be talking about. So from the flyby, we know something about the present day inventory or amount of various volatile ices on Pluto's surface and atmosphere. So we know that to the level of the flyby, so we know what's happening on the encounter hemisphere and what was happening exactly at the time of the flyby. And what I'll talk about mostly in this talk is what could have been lost from Pluto over time. And then in the second half, Bill will come in and talk about what we think the primordial inventory of Pluto could have been, so what it initially started with. So if we add up these first two reservoirs, you get the primordial inventory. So in terms of atmospheric escape, so particles subliming from the surface ices, entering the atmosphere, and then eventually leaving Pluto's gravitational well. There were expectations about what that would be like pre-flyby. So some of the first models of atmospheric escape from Pluto suggested that Pluto might be in what we call the hydrodynamic regime. So this is when there's like a bulk fluid flow of atmospheric material leaving the atmosphere. And so some various papers made estimates first for methane, since that was the first known atmospheric constituent, or the first known species on Pluto, volatile species on Pluto, and then later for nitrogen as well. And so you can see kind of the order of magnitude there. Interestingly, this is the same 10 to the 27 from James's talk, but this is in molecules escaping per second, not joules. Some other people added to this field by coming up with this idea of energy-limited escape. So essentially, the escaping particles can't carry off any more energy than what is driving their escape. So in this in this scenario, it's like solar insolation and UV insolation that's driving the escape. And so you can use that as kind of an upper limit for escape that might be happening. And so you can see you get similar escape rates for both nitrogen and methane when you use that framework. And then more recently, there have been DSMC models, which is direct simulation Monte Carlo models. And so those kind of make no prior assumption about the mechanism of escape, but just track the particles. And they found that the escape rates that they find from those models are kind of more similar to the gene's escape regime. So this is the sort of boiling off of the atmosphere in contrast to bulk fluid flow and hydrodynamic escape. And so you get kind of lower escape rates predicted from these DSMC models. And it turns out that once we got the results from the flyby, that escape was much, much lower than what was predicted previously. So you can see here in the two boxes on the right, those escape rates are orders of magnitude lower than what the pre-flyby predictions were. And the reason for that is Pluto's cold upper atmosphere. So the figure that I'm showing here on the left is from Randy's post-flyby paper. And if you look at that orange dashed line and orange solid line, that's the upper atmosphere temperature on Pluto. And it's much lower. The solid line is what was observed by New Horizons, and it's much lower than the dashed line, which was the prediction. And so that really changed the level of the atmosphere at the exobase, where escape is happening from, and resulted in much lower escape rates than pre-flyby predictions. But we've already talked a little bit about how Pluto might have evolved over the history of the solar system in some of the earlier talks this morning. And so we know that past conditions on Pluto were different. And so as Will alluded to in his talk, we should not assume that these escape rates were constant over the whole age of the solar system. So we can try to understand how these different past conditions evolved over time. So the first one we'll talk about is the fact that the sun was different. So the sun bolometrically, kind of overall, was less bright than it is currently. So that's the left plot there, showing that the sun was 70% as bright as it is currently in the very early time of the solar system. But if you look at UV wavelengths, so that's what's shown in the figure on the right, the UV wavelengths were like 100 times as bright or even brighter than they are in the present day. So this like UV solar flux was incredibly strong when the sun was very young and just entering the main sequence. And so these two effects from the sun both influence escape rates, but they do so in different ways. Pluto also had more internal radiogenic heat back at the time of its formation. The various nuclides were providing more heat flux than they do at the present day. So this is something like maybe 8 or a few times higher than the present day radiogenic heat flux. So again, that affects the temperature of the surface ices and therefore the atmospheric escape rate. And then a big difference for Pluto long ago versus Pluto in the present day is its orbit. So Pluto might have formed closer to the sun, maybe around 25 AU, and then was pushed outwards during giant planet migration. So specifically when the orbit of Neptune was extending outwards, Pluto and the other Plutinos and really the other Kuiper Belt objects just got tossed around the solar system and had very different orbits than their present day. So it seems like this little animation is not going to play. Normally this blinks through all the different simulated Plutino orbits, but you can see at least one highlighted here in black, and then the gray shows kind of the variety that we investigated for this work. So we took these simulated Plutino orbit evolutions along with the early sun and early Pluto radiogenic heat fluxes in order to understand how escape rate might have changed over the whole age of the solar system from CAI condensation all the way to the present day. And so we did this within an enhanced genes escape framework. So this is an escape rate that is slightly higher than what is predicted by genes escape, and this was informed by some of the DSMC models. And so we took the present day escape rate, which is shown there, 10 to the 22 nitrogen molecules per second, and we scaled it, accounting for those differences in early Pluto in order to calculate an escape rate over Pluto's entire history. And I will say that we had to make a lot of assumptions along the way. We don't know what was happening on Pluto 4 billion years ago, 4.5 billion years ago. So we've tried to always make the choice that drives escape faster. So we've tried to always make the choice when we had to choose between different assumptions. We always made the choice that would lead to a larger escape rate. So we were trying to calculate kind of an upper limit of the escape rate over the age of the solar system. And so what we find when we apply that enhanced genes escape rate over the age of the solar system is we get an escape rate evolution that looks something like this. So this is showing escape rate on the vertical axis and time since the start of the solar system on the y-axis. So this is only the first 100 million years or so of solar system history. This is really when exciting things were happening at Pluto, and then it kind of calms down after this. And what we found in this work is that the sort of the median or the average simulated Plutino loses something like 100 centimeters of nitrogen to escape during this 100 million year time period, which I'll show you in a couple slides is not very much at all. Sputnik has something like 40 to 400 meters global equivalent layer of nitrogen. So this 100 centimeters is a drop in the bucket. And so even when accounting for these different early behaviors, of Pluto and the sun, escape is just not a significant loss of nitrogen. And at this point, for various reasons, Leslie and I were really hoping to find the opposite answer. We were really looking for a large loss of nitrogen early on in Pluto's history. So we didn't find it in atmospheric escape, so we looked at some other loss mechanisms that could have been active during this time period to see if maybe they represented this large loss of nitrogen that we were looking for. The two other loss mechanisms that we looked at are photochemical destruction. So this is when an incoming solar UV photon strikes a nitrogen N2 molecule, breaks it apart, and in Pluto's atmosphere and on the surface, this is an irreversible process, so it represents like an irreversible loss of N2 molecules. So we look at that as a loss mechanism, as well as impacts. So when an impact comes in and hits Pluto, there's some amount of atmosphere that gets lost just through blow-off that happens. But we also wanted to account for the fact that the things impacting Pluto have similar composition to Pluto, so they also are a source of nitrogen, so we accounted for both of those effects. And if we look at the photochemical destruction, we have estimates for the photochemical destruction rate for Pluto at the present day, and then we simply scaled that present day rate based on these three factors here. So when Pluto's atmosphere is more extended, Pluto represents like a larger cross section. And so we account for that effect, and then we also account for both the early sun behavior and the varying heliocentric distance as Pluto is being pushed outwards. And what we find when we look at photochemistry is that it's a larger effect than atmospheric escape, so something like 400 centimeters global equivalent layer of loss of nitrogen. But I will show you again in a couple slides, that's actually still just a drop in the bucket compared to what's presently in Sputnik Planitia. So photochemistry was not the holy grail of nitrogen loss on Pluto. It was also fairly minimal over the age of the solar system. And then we looked at impacts as well, and so we accounted for the fact that during the wild years on Pluto, this very early time period in Pluto's history, impacts were much more common. There was just a lot of debris hanging out in this part of the solar system, and so we account for the higher impact rate and account for how much impacts would both deliver to Pluto, how much nitrogen they would deliver, and how much they would remove. And I won't go through the details of this figure, but the punchline that we found is that impacts are actually a source of nitrogen rather than a loss. So because Pluto's atmosphere is relatively thin, you can only remove so much nitrogen for every impact. And so for most impactors, they deliver more nitrogen than they remove. So the sort of conclusion of all of this work is that Pluto hasn't really lost much of its initial nitrogen. We looked at these three different mechanisms: atmospheric escape, photochemical destruction, and impact removal. And what we found is that the integrated effect of those mechanisms over the entire 4.5 billion years of the solar system is less than the amount of nitrogen that is currently in Sputnik Planitia today. So the red lines shown in these whisker plots on the right, all of the red lines are way lower than the amount of nitrogen that's currently in Sputnik Planitia. So the conclusion from this work, like I said, is that Pluto's primordial nitrogen inventory was not necessarily particularly different than its present-day inventory. This is a wall of text, and I just wanted to be clear that there are lots of caveats and assumptions to that conclusion. So I've listed some of them here. I'm sure there are more. We've only looked at a few loss mechanisms. We've only looked at nitrogen. We had to make assumptions about the form of nitrogen that it's in N2 originally. There are lots of assumptions we had to make about the effect of methane. You'll notice that we didn't try to estimate the methane escape rate at all. We only looked at nitrogen. So there's lots of more work still to be done. But at this point in time, that's our conclusion, that even accounting for the early sun and early Pluto behavior, not much nitrogen was lost. This is not my work anymore, but I thought I should mention some things that are happening as we look forward. Especially if you're familiar with like the Martian atmospheric escape, a hot topic to think about is isotopes. And so isotopic ratios are often used to infer the amount of loss of a particular volatile species over time, because most loss mechanisms fractionate by mass, and so the heavier isotope will be preferentially retained. In practice, this is tough to do for various reasons, but various people are starting to do it for Pluto. So specifically, Emmanuel Lelouch has used both JWST and ALMA to get estimates of isotopic ratios for D to H, for deuterium to hydrogen, as well as for the two isotopes of nitrogen, so nitrogen 14 to 15. And Krasnopolsky has also used his model to understand the nitrogen isotope ratio as well. So there's still a lot more work to do here. I think this is kind of just the start of isotope ratios on Pluto, but as observers continue to make predictions or to make measurements of these isotopic ratios, people like Chris Glein can tell us what that means for the chemical history of Pluto and the material that it started with, and how much has been lost over time. So I think we'll hear more about this maybe in Chris's talk this afternoon, but I might be putting words in his mouth. Okay, so yeah, I'll just drop back to my conclusion slide really quickly. I've said it a couple times now. The punchline is that from this analysis, we don't think that past volatile loss was very significant on Pluto, but lots of caveats to that, and I look forward to seeing more isotopic ratio measurements in the future to understand more details about how much nitrogen and methane Pluto started with. So with that, I will pass it over to Bill McKinnon for the second half of this talk.